Today we are doing we're going to look at subsystems and commands, the framework through WPILib. The slides I'm using today were produced largely by Matt Lithgow of Team Triple Helix. I've modified them, and I'll be adding in the commentary and everything as well. But thank you to him for producing it and sharing it with me to make this a lot easier on me. Okay, so we kind of have to explain what the framework is and why we have it first before we even look at like how it's implemented. So on the actual physical robot, right, we have a driver station, which is where the driver actually like pushes buttons and has the controls and everything, right? We have a physical way to interact with the controls. We have the electrical signals, so we have like the radio waves, and we have the actual like the robo-rio that's doing a bunch of computation and things, and it's sending commands to all the motors. And then we have the actual robot that's doing things, right? We have an intake, we have a drivetrain, we have all this stuff actually happening in the physical world. And this is all happening physically in real life, right? In our program, we basically want to have all of these things in a way that we can refer to them and use them. So we're going to do that by having what we're going to call a logical robot. So here we have the operator interface. So this is the variables and objects that represent what the driver station is doing, all the buttons and things that are being pressed. We have all of our actual logic that takes place to figure out what should the robot actually do, right? So this is after we know what buttons are pressed, we know all that stuff, what's actually going to happen, how does that logic flow. In our previous example, this was kind of those if-else statements that you were writing to determine what was actually going to happen with the robot. And then we have the actual output to the robot to make all of the motors and everything move, right? We get the final output of sending actual signals to the robot's motion. Okay, so in command-based programming, it gets built up in a few different ways, but we kind of get to represent our logical robot a little bit easier, and it allows, one of the really nice things that it allows for us to section things off, so multiple people can be working on things. So we can have different sections of the robot. We're all not working in the same big file. So that's one of the big advantages. So here we have the subsystems of the robot. These are all the different parts of the robot that could be programmed. Then we have commands that act on those subsystems. So we need to be telling each subsystem what they should be doing. So what should the drivetrain be doing? What should the climber be doing? What should the intake be doing? And then we have the operator interface that is like the button. So this would be like if the driver was pushing the Y button and it started intaking a game piece because of that. So when we come back and look at our logical robot, we can see that the actual physical robot is basically the subsystem. So those are the things that are happening on the robot. That's kind of what the robot's able to do, and a representation of the physical parts of the robot. We have the commands, which are all the things, which is basically what we're telling the actual robot pieces to do, the subsystems. So we'll have a variety of commands. We won't just have these three, right? The climber doesn't only have a do nothing command. There'd have multiple things that each of these different subsystems could be doing. And so those are the commands that we'll write. And then you have the operator interface, which would be all of the potential buttons in every way that the operator is able to interact with the robot. So a group of subsystems defines the entire robot. So every part of the robot will either be a part of a subsystem or will have its own subsystem. So if we were going to add something to the robot, so if our robot didn't just have a drivetrain, intake, and climber, say it had a launcher as well, there'd be another subsystem block that would be for launcher. You can have a subsystem for any part of the robot that's going to physically do something. They're very similar to our design subsystems because we break out how we actually design and CAD the robot into subsystems as well. So there's a very similar logic there into how we do that. There's some overlap sometimes, and they're not exactly the same between the design ones and the programming ones. Kind of depends on how different things interact. But you can kind of think of them the same way. So inside of each subsystem, so like this is the intake subsystem. So just like there's this intake block has stuff inside of it, and that would be everything that makes up our intake, right? So with the everybody intake that we talked about last week, we would have a motor controller to control the actual intake spinning in or spinning out the balls. We'd have a pneumatic solenoid to raise and lower the intake up and down on the ground. And then inside of that, you also have behaviors that the intake can do, but it's really important to understand that these aren't commands. So these are going to be really simple, and they're not going to be grouped. They're not going to be multiple things at once. They're going to be really, really simple. So the behaviors are things like raise or lower the intake, spin the intake motor, but they're not necessarily directly what the operator is going to tell it to do necessarily. A command can be allowed to get a lot more complex. Sometimes the command is just setting a single behavior, like that's part of it, and it will happen. But a lot of times the commands will get built out and interact with a lot more of these things at one time, possibly. So we want to differentiate behaviors from commands. So just because you write a behavior doesn't mean you have the command written yet, and just because you write a command doesn't mean that the behavior has to exist yet either. Okay. So these are the electrical components that would make it up. So you'd have motor controller solenoids. If there was any sensors, so if whatever the subsystem was, if it had a way to know if a ball was intaked already, if it had a way to know how fast the intake was spinning, or if it was a launcher, how fast the launcher was spinning, any sort of sensor that's associated with that subsystem is included here as well. And then those are the parts of the behavior. So these would be methods that are written inside that subsystem class, which we'll see in the examples later. But that's how you would be able to define these behaviors. So commands allow you to group multiple behaviors or use different parts of the subsystem. So instead of having to individually tell the intake to spin in and lower the intake, you can have a single command such as intake balls that will tell the intake to go to the floor and tell it to spin the balls in at the same time. So we can make things much closer to what we want the driver to actually be able to do. So they can have a single button that does these things, or a single way to interact with the actual commands that we want to be given the robot. And they can be a little bit less detailed in what they have to do. So in our code last week, to intake the balls, they would have had to hit one button to lower the intake and another button to spin the intake in, which is a little bit more complicated than we want them to do. We'd rather have a single button that does both of those things. And this whole thing allows us to write some code that we can then reuse over and over again, without having to constantly be tweaking multiple different things. So we're copying and pasting or anything like that. It allows us to write it once and use it in a variety of places. Each command is controlling its assigned subsystem. So you wouldn't have one command that is controlling, you wouldn't write a drive command that also controls the intake. It's possible to have a command that controls multiple things, but it's super rare. Most of the time, you're going to write a specific command for a specific subsystem. So the drivetrain's almost always running on the command that's just drive with controller so that the driver is able to operate it. In our past robots, we've had other commands that would take over, that would be used on the drivetrain at different times. So instead of drive with controller, we had in the 2019 game where we had to put the ball and hatch panel into the big rocket ships, we had specific commands that would auto drive the robot into the right spot. So it would use its vision system to auto align the robot, and it would drive forward to score the object and basically take control. It wouldn't, even if you were moving the joysticks, the robot wouldn't do anything because that command wasn't running anymore. The command that had it automatically trying to score would be running at that time. So you can have different commands running on different subsystems at different points. So same with intake. Sometimes you might be intaking game piece. Sometimes you might not be doing anything. Sometimes it might just be intake is stopped and stowed away. Other times it might be ejecting a ball. The climber could be climbing or it could not be climbing. And these get more complicated as you get more and more complex robots and they're doing a variety of different tasks. Okay, so the operator interface defines which buttons go to which commands and how they're triggered. So there's a variety of different ways that you can like start a command based on different buttons. You can have them start when you press it. So all you have to do is press it once, and something will continue to happen until you somehow tell it to stop. Whether you have to press that button again or a different button. You can have a command that only runs while the button is held. So there's some commands where you have to just hold Y to intake, because that would make sense, right? You want to be holding that button the entire time, and then when you let go, it all stops. There are commands that work based on, you can stop them based on some sensor value. Say you've climbed all the way up, and it would automatically stop you. You can do things when it's released, so a certain command can happen after you actually let go of a button. There's a whole lot of different things you can use to choose when a command should run. The command scheduler is what actually keeps track of all of this stuff. So if you have so it's basically holding this kind of like this window here, and it says, okay, right now drive with controllers running, right now intake game piece is running, and the climber is doing nothing. And then if I hit a different button and tell it to eject game pieces, the command scheduler is what kind of allows us to do that. So I'm going to walk through how that works in just a second. It checks if new commands should be started or stopped based on the operator interface, or if some other part of our code is starting or stopping a command. And then the most important thing the scheduler does is it restricts subsystems to being able to only run by one command at a time. So we don't want to have a case where for some reason we're hitting two different buttons to do different things on the intake, and now instead of the intake either spinning into intake balls or spinning out to eject them, it's like going back and forth or flipping around or not quite doing what we actually want it to do just because we gave it multiple commands. So the scheduler helps solve all of that. It makes it so only one command is running at a time per subsystem, so we can have a better idea of what's actually happening with the robot. So with the command scheduler, this is what's currently happening. So we have the drive with controller running and then drivetrain, and currently we're on retract intake. So the intake is up and it's stopped and it's just in its normal default state. When the operator presses the Y button, if we've mapped that to be intake balls, intake game pieces, the scheduler will see that. It will basically be like, okay, now it's time to start intake game pieces. So then it'll try to move it into the command for intake, except it sees that retract intake is already running. So it'll stop the retract intake command. So it'll tell it you're no longer running, and it'll move intake game piece into, it'll let intake game piece take control of the intake and do whatever it's programmed to do. Once we let go of Y, so once the driver lets go of Y, if it was set up to where it's only running while held, the scheduler would cancel intake game piece. It would be like, okay, we're no longer intaking, the driver let go of the button. And it would, it'll check to see if intake has what's called a default command, which is something that gets run when nothing else is being told to run. Most of the time you want some sort of default command for most of your subsystems. You want it to get put back into a state where the motors are stopped, where it's in some safe position, so it's not just hanging outside the robot or things. So in this case, the default command for intake would be something like retract intake, where it's back up. It's back up, it's stored in the robot, the intake is off. And so that's what we'd want to happen once no other command is running it. So once we tell intake game pieces to stop, because we've let go of that button, the scheduler will automatically run whatever the default command is for that subsystem. Okay. In review, the command scheduler watches for button presses. It then starts the new commands and stops old commands for us. And the running commands tell the subsystem what to do. So we always want to make sure we have, most of the time we want to make sure we have some command running on the subsystem. Normally that command is going to be to stop it in some way, make sure nothing is running. It's all in like a safe environment and whatever kind of our default mode for that subsystem is. You also sometimes have default commands that are more like manual operation. So the default command for drivetrain is normally drive with controller. We want, anytime the robot is enabled, we want, if we move the joysticks, we want the driver to be able to drive the robot around. So that is what the default command is for that subsystem. Other times, ones like the climber are basically just making sure the climber motor's not running at all, and that would be the default command. Okay, we're going to take a look at sample code that I have set up for, it's the same, basically it does the exact same stuff that our EveryBot code did last week, except it now uses the command and subsystem structure. Let me exit out of some files real fast. We have too many things open, and we'll kind of walk through how this all looks. Okay, so let's see. All right, so some of this should look familiar. So last week we had a robot.java and we had a robot container.java. And all of our code last week in the last lesson was in robot container. So we had, we defined a controller, and we defined like the motors specifically for the drivetrain intake and everything right inside of this class. With the command and subsystem structure, we break everything out into their own files. So it's a little bit easier to keep organized. We can have different people working on different subsystems and different commands. And we kind of know what's gotten updated and what's been changed. And we can keep things a lot more organized than having everything written out in one big file. It's a little bit more complicated because you have to find, you kind of have to know where things are, or you're not just looking in the exact same file every time. And like I said, all of this code basically does the exact same, or pretty close to the same stuff as last time, but it's built in a way that allows us to add more stuff easily and add more features and more commands and basically make the robot work a lot better. But it does add some complication, but it's why we use it, because we end up needing a lot more complication than just that simple code we were looking at last week. So starting at the beginning, let me make it a little bit easier for everyone to see. Okay. So robot container has a controller, so it's just like an Xbox controller. In this case, we're using a specific Xbox controller class that Spectrum has written. So the Spectrum Xbox controller class does a few things in the background. You don't need to worry about it too much, and we'll see kind of how it makes it easier. But basically, it lets us access some of the buttons on the controller a little bit easier than what we had to do last week. And it's just code that we've written to make our lives easier when we're programming certain parts of the robot. And then here is where we start actually defining subsystems. So this robot right now has 3 subsystems. It has a drivetrain, an intake, and a climber. So there's an instance of each of these inside of this robot container class. So if we look at the intake subsystem, so if we come to this file, so over on the left, we have our kind of our file manager. There's a subsystems folder, and one of those is intake. And so we can see a lot of the same code from last week. So we had Victor SP motor equals Victor SP. Last week, this was like intake motor, but since we're in our own intake class, we don't need to do that anymore, right? Because this can just be motor, and we know it's the intake motor because we're in the intake class. New Victor SP, and then last week, this was just a number. But as we build things out and we get a little bit more complicated, it gets hard to figure out what values have already been used, kind of where the hardware mapping, what's plugged into where, like what those numbers absolutely represent is like what port on the RoboRio things are plugged into. So we have a class that all it is called constants, and it just has things that are constant numbers. So this, all it does is map 0 to K left drive motor, 1 to K right drive motor, and kind of those same things that we were doing last week, but it lets us do it all in one place. So if we need to go and edit it, we can very easily change where a motor or something is plugged in, and we know we can just do it right in this file, and then all of the subsystems just refer to things that were written out in here. So I haven't written out climber for this robot yet, but there would be a climber motor, and any of the digital inputs, if we had sensors on it or anything else, those would all get defined in here as well. So just like we did motor, we have a solenoid. Again, last week it was intake pneumatic, but since it's in the intake class, we don't need to have that intake part. And then same with the constants, it's just pulling that value from some place where we know we can edit it easily. The same sendable registry things that we had last week that aren't important to know what they do, but just know that they're useful for the smart dashboard or the shuffleboard. So those are there again in the constructor for this class. So this is that method that runs when you make an instance of this class intake. So right here where we do that new intake, this is when that's going to get run. And then the set default command is how we tell it what the default command for this intake is. And in this case, it's stop intake. We'll look at what the command looks like in just a second. But here, basically, we define very early what happens if nothing else is running on the subsystem. So we basically tell it always stop if nothing else is telling you something to do. Okay. So inside of here, so we've basically defined the hardware. So these are the only two parts of the actual hardware for the electrical system that we need is motor and pneumatic. So then we basically need to tell it, how do we interact with those things? So this is the behaviors part I was talking about earlier. So these aren't commands, these are just methods that allow us to actually interact with them. And these are what the commands will interact with specifically to allow us to actually do things. So we have a few commands we have a few behaviors, few methods for the motor portion. So we have one that is just allows us to access the motor's specific set. So if we wanted to set a speed directly for the motor, if there was some reason why we wanted to go at a specific speed, one of our commands could use this set method to do that, and it would pass in a double, and it would just pass it straight to the actual motor set command like we were doing last week. But then there's other times where we want to make it a little bit more convenient for our code. So if we have, so there may be multiple times where we're intaking balls in different commands. So we can have a method that's just called intake, and that we set the value right here. So if we have this value set to 1.0 right now, and it's intaking, if at some point when we're working on the robot, we realize, ooh, that's spinning a little too fast for the intake, maybe it's causing some sort of problem, we can come in and we can edit this number right here and slow it down. So we could make it like 0.8. And then anywhere else where we were telling it to intake, in any of our commands that had intaking for some reason, it would automatically get it would get slowed down in all of those commands, because they would all be using this intake method So again, it allows us to kind of like have a single place to edit stuff, even though it's getting used in multiple places in the robot. Eject is just the opposite, so it's the -1 version, so it has the roller spinning backwards. Intake and eject are also useful in that you don't have to worry about direction or anything. If your command uses the intake one, you know that that's always going to be spinning the balls in, even if maybe the number value or something is backwards for some reason. Um, you know you can just always configure it in here and make it correct. And then finally, we have a stop, which is always a good thing to have, so we can tell the motor just to stop spinning. Um, Similarly, we have the same um, very basic methods to tell the intake to either be up or the intake to be down. So nothing really complicated there, but it allows us to get a little bit closer to um, English, so we know exactly what this method is doing, right? Raise intake is easier to understand than dot set false. It's possible that if you configured your robot differently, dot set false could be down and dot set true could be up. So here, if for some reason that happened, you would just have to change these values here and not have to change them everywhere in your code, right? Your code could continue to use this raise intake method, and even if these flip for some reason because your pneumatics got changed around, something happened on the actual hardware, um, you could swap these values because maybe it's now up is down and down is up. But then everywhere else in your code, raise intake would still be what you wanted it to write, and you would only have to change it in one place, and everything would start working again. Okay, so let's look at what a command looks like. So the intake commands, they have a couple different things already established for us. There's several methods that a command needs to have, basically. And we're going to go through, we'll probably go through all of this again next week as we start doing more examples on it. But so the intake balls class is a very simple command. It has a constructor that all it does is add the requirement. So it basically tells the scheduler that it's the only thing that can be using the intake. So here it's basically just saying, okay, I need the intake to run. If anything else is running, if anything else is using the intake when I'm being told to run, please stop it and then let me run. So that's how the scheduler knows what to stop when intake ball starts running. It has an initialize method. Initialize runs once right when we call it. So as soon as we hit the button, it'll run one time, and then that'll be it. So for things like the pneumatics, that's totally fine. So we can have lower intake happen once, because until we tell it to do something else, it'll just stay down. So we'll tell it to lower, and then during execute, it happens over and over again. So as long as we're holding that button, very, very quickly, multiple times a second, it will continue to run anything that's in this method. So in that case, we'll tell it to keep intaking the ball over and over and over again so that the motor continues to spin and trying to intake balls. And then the final method is to what happens. Basically, it tells it, what do I do once I'm being told to stop? So as soon as we let go of a button that's commanding this to exist, we want to make sure that we basically clean up the actions that we did. You don't always have to, because it's going to have a default method that tells it to stop too, but it's a little bit safer if you do this. It doesn't hurt anything to do it this way. So once you end, we're going to tell it to bring the intake back up, and we're going to tell the motor to stop. And so you can see we're using the methods that we defined inside of intake, right? So we have this intake, this eject, this stop, raise intake, lower intake. So all that the command is doing is just using those methods directly. We're not directly talking to the motors or anything like that. We're just using those simple methods that we wrote out in here, and that makes it really easy to figure out what they should be doing too, because the VS Code auto-complete stuff for you. So if I just start with the dot there, it shows me all of the different methods. So I can start typing stop and it completes it for me. So that makes it really simple to write code and kind of know what each of the different subsystems is able to do. And then you can add things into the subsystems to make it easy for your commands to do things as well. Okay. All right, so drivetrain is very similar. It just has a arcade drive class, so I just made it the same name as what the arcade one was anyway. And then it has a command drive that just gets the controller sticks and passes them to that class. And that's all it does. And inside a drivetrain, that drive command is its default command. So anytime that anything is happening, if nothing else is happening on drive or on the drivetrain, the drive command is running. So we don't have to even tell the drive command to start. It'll just automatically start because it's the default command. So going back into robot container real fast, we have this configure button bindings method that gets called right when robot container gets started. And that is where we actually kind of define our operator interface. So here we have a reference to the controller, and it's going to use the right bumper, and it says while held. So that's anytime that we're actually pressing the button and it's held down. We're going to run intake balls. So it's going to start that command when the right bumper is held down. And on the left bumper, it's going to do the same thing for eject balls. So that's all we have to do to get the command scheduler to start basically watching for those button presses and acting on them. So anytime that the right bumper is held down, intake balls will be running, and as soon as we release it, the command scheduler will know it's not pressed anymore. It'll stop that command, and it'll have the intake run its default command if nothing else is running. So it handles all of that scheduling and things for us, so we're not writing a bunch of if statements and things to try to overlap and figure out what all is going to work and what isn't. It kind of does a lot of that work for us. So we can see in the simulator if we want. All right, so we can start the simulator just like we did before. Let me make it so you can see the simulator. All right, so if I switch it over to teleoperated mode, there we go. And we have shuffleboard. So now if I do the same thing as before, I can move the left stick forward, it goes forward, backwards, left, right. And now I can do multiple things on the same button. So now my right bumper, instead of before where we had to hit both hit both the left bumper and the right bumper to have the intake go down and intake. Now I can do that all in a single button. And then as soon as I let go, it stops. And if I hit the left bumper, it goes to -1. So it'd be like spitting out balls to score them. So you can have multiple things linked to a command very easily. And like I said, this isn't anything new. So we didn't make any new functions. It's not doing anything. The actual outputs are basically all the same. We just added in that framework layer that allows us to do the expansion a lot easier and to make a lot more abilities into our code than we had before. Okay, how am I doing on time? All right, so I didn't write the climber stuff yet, so we're going to do that together so that I can give you an idea of kind of how this works. So our climber subsystem exists, except it's completely empty. So from here, we're going to do a lot of pattern matching just like we did before, except now we're in different files. So the climber is relatively similar to the intake. It has a motor. So I'm going to pull this and I'm just going to copy. So motor, no, extra O got put in there. All right. So anytime in VS Code, if you get these like red squiggly lines, a lot of the time it's just because you don't have the imports. So if you click on it, come over to this light bulb, the first option is normally correct. It's not always. Read it and see if it sounds like what you want it to do. It just says import Victor SP. So instead of having to type out the import, it'll just do it for us. Same with this, constants, doesn't know where that is yet. So we do import constants from FRC robot. It does it for us. So this motor is fine because we know it's the climber motor, but here's less good, right? So it's asking for the intake motor. That's not the right one. So we can come here and go to definition, and that'll bring up our constants file. And now we can add a climber section, and we can very quickly add a climber motor. Save. We can go back in here. And then if I do that, it'll automatically have it ready to autocomplete for me. And now we've set up that climber motor. It's ready to go. If we look at intake again, we can see in here, the next step was adding our sendable registry. So I can again just make a copy. It doesn't have it imported either, so I'm just going to add the import. And then motor, and its new name is climber motor. And then the last thing it needs is a default command. We're going to add this after we actually make the command. Since we don't have a command yet, we can't quite add a default command. Okay, so now we need to figure out what the climber is going to actually do, right? Because we have these different methods here. So our climber motor behavior, something like that. So our climber will be able to, we normally have some method that allows us just to completely set it. So similar to what we would do here, it actually can be the exact same method. Since none of this was specifically set for intake before, this will do the same thing that we want it to. So it'll allow us to set the climber motor directly if we need to set the speed in one of our commands for some reason. But then these ones would need to be different, right? Intake and eject don't make any sense on the climber. So we'll write our own for, we normally have like a climb. And here we just have some speed that we want to climb at. Maybe we want to actually climb full speed. And then we can have some other behavior. We can name it whatever we want, unclimb, backwards climb. It doesn't really matter as long as we know kind of what it means. And this one we probably want to go slower. So maybe it's only doing, maybe it's going real slow so that we don't come down really hard when we try to go the other way. You could also have one for like raise climber, which could be a different button or a different command where we want to bring the stick up and be ready to grab the pole. So maybe that one you want to be fast. And that it can all depend on what direction we want things to go. Maybe this is on the robot, these might be the other way, so we would invert them. So you could change which ones have the negative sign if the motor is going a different direction. And all of that can be done right here. We kind of know where any of those tweaks and changes will be. They're always in the subsystem class itself. And anything that's kind of related to the actual hardware gets put into here. So if we needed to actually make a subsystem now, there's a couple different ways to do that. So I don't have a class for that yet. So I could either, I could copy one. So I could copy one of these, paste it, and kind of delete and edit what I want, or you can start from scratch. So if I right click on the commands folder, there's this option down here for create a new class command. And that brings us up to that same like WPI lib window, and it allows us to create new things. And I know I want to create a command, so I'm going to start typing command. And we're using, for any of our command things, we're using this parenthesis new. There's two different systems that got implemented. We moved to the new system last year. So anytime if you have a choice between old and new for any of our things, just choose new. And then it asks for the name. So the most obvious climb command is climb. So we normally have one like that, and that's the easiest one for us to make today. And it adds in all of this stuff for us. So you don't have to remember that you need an initialize, execute, etc. It kind of does all of that for you, and we just have to fill it in. Okay, so we just have to do add requirements, which is how we tell it which subsystem is important, right? And so that's robot container dot climber. So it has its requirement now, so it knows that anytime climb is running, nothing else, no other command will be running on the climber subsystem. And for execute, we just want to call the climb method from our climber class. So we'll do robot container.climber, because we do want to make sure we're referring to the instance of climber that is in robot container. So we want to make sure we're referring to this small c climber and not big C climber, which is just the class and not the instance of the class. There's some other conventions that people use to make that a little bit easier. We never have. We just leave it as the uppercase, lowercase. It works well enough. And if you do it wrong, Java just yells at you and tells you, right, it just gives you the error, and it doesn't let you continue. Climber dot climb. So a lot of times you do have things that are the same method or the same name, and it can be confusing. So if it starts getting confusing, it's totally fine to rename things to make them less confusing. So if I went in here and I renamed this to something like climber command, that would be fine. You do have to rename it in here as well. It'll auto rename there. So now this is climber command, and it's different, or climb command, and it's different from the climb method if that's getting confusing. But you are able to kind of use the same word in different places as long as it's in a different use case, basically. And then this end command is basically telling it what do we want to do once we're no longer climbing. And in that case, we want it to stop. So we'll do this, and we'll do, did we not make a stop? What happened? Oh, we didn't make a stop. That seems important. See, we forgot to make a stop. All right, public void stop. And it will call motor.stop. Okay. So now we have a stop. So I can save that. And when I come back here, I should be able to stop. Okay. So that's really, again, that's really important. We want to make sure that once the command's actually over, the motor does stop moving. And that should largely do what we want. At the moment, climber doesn't have a default command, but that's fine. Normally, we would eventually give it some default command that would tell it to stop. But for the purposes of today, we're just going to go ahead and add the button and not write out that whole extra command. So to have the button tell it to do it, we'll do controller We can make any command we want. How about A button? While held, new. Did I feel like I did. Oh, I did something wrong. So our methods or our actual class name should always be capitalized, and I have this as lowercase. So I'm going to rename this to be capital letters. Does it matter to me? Okay. Renaming that element is not supported. Why not? Okay. Well, you're being weird. All right, that should be fine. Okay. So then, yeah, climb command, it auto-completed for me. Add the semicolon, and it seems like we're okay. So if I build this, and assuming I didn't forget something, if I go ahead and do simulate, we should be able to press the A button and have the climber motor run, hopefully. All right, so if I enter teleop mode, I press A. Over here, we can see that we get that 1.0 value, so we can see that that works. And here, maybe, let's see. There we go, climber motor, and when I press A, we get that 1.0 value. So now we have that command scheduled, and every time I press it or release it, it does what we want. So we could add a host of other commands. We could have something to where we put it on a joystick value or the D-pad values. You have a lot of different options in here on how we can control our various subsystems. But this whole sort of structure we went over today is what lets us very easily split up our work and keep things organized so that if we get an error somewhere, we can easily figure out exactly where it is, so we know what files things are in. We can know where to change things and where to adjust things. And ideally, we don't have a lot of code in other places interrupting those different things. So if something's broken on the intake, we know that it's either in the intake subsystem file or it's in one of the commands that's driving the intake. So it's much easier to kind of debug and find where there are errors in our code. Okay, so I think that's all we're going to cover today.